What is up, Patreons? Let's continue with a blocker or blockchain and Golang. So, it's going to be maybe a shorter episode, but a very direct episode, a very specific episode. We are going to implement the Merkletree. So what is a Merkletree? Yes, here. So basically, a Merkletree is basically this one, right? So we're going to have different nodes, right? And then it's basically a cryptographical way to determine the, how do you call it? The integrity of the tree you constructed, right? And you're going to have a root hash, and the root hash is going to be some calculation. It doesn't really actually matter how it's implemented inside. That's not the point of this video, right? You can easily make a Merkletree yourself, and there are different Merkletrees with different behaviors, but it doesn't really matter at all. The only thing we care about is that how we're going to use this thing, right? So basically, if we see the example, we're going to make a list, right? It's very small, I know. This is going to be very, very small. Actually, to be honest, let me copy this. Let me copy this, and let me open up this thing. Let's go to main real quick, and let's paste it in here for some reason. I know it's a bit scuffed, but hey, right? So we're going to have this list here, right? We're going to make a list. It's going to be a Merkletree content, apparently. And then we're going to basically append to this list, we're going to append transactions, transaction hashes, or whatever we want. Transaction hashes would be, in my opinion, good. And we're going to append all. So for each block, we are going to create a list, right? A Merkletree. Then we're going to append all the transactions into that list. And then we're going to basically calculate the Merkle root, right? And it's the Merkle root which we need, right? So basically, each time somebody is going to get, if each time somebody is going to fetch a block and he wants to verify that, he needs to verify the Merkle root, where it's basically the root of all transactions, right? So the Merkle root is going to be, I will show you, right? Let's open up types proto here, and we have a root hash, right? It's going to be the Merkle root of the transactions, right? TXX, actually better maybe, right? Other transactions. So basically what we need to do is we're going to take this root hash, we're going to basically construct our own Merkletree based on the transaction hashes, and then we're going to calculate the Merkle root, and then we're going to compare those two with each other, right? And if it's fine, then we have a valid root hash, or Merkle root, whatever you want to call it. As long as you understand, it's a fine. All right. So let's go to main and let's delete this shenanigans real quick here, eh? So we're gonna delete this. Hop, hop, hop. Fine. Where are we setting this thing? So I think if you go to types block, actually, block here, right? So we have verify block, sign block, hash block. Do we have something like I'm thinking, because there is no way we create a block, to be honest. Let me open up some tests to see how we're going to construct this chain test, right? So we have a random block. We're going to sign that block. We don't, are we using random block? Test add block with TX. So we create a random block. We're gonna, yes, what I'm gonna do here real quick is I'm gonna do some stuff actually. I'm gonna do some stuff. I want to call something like this, right? So we're going to have something like a finalize block, which is going to be a B, a proto block. Maybe this video is going to be longer than expected. Finalize block is not going to do anything, and finalize block is basically going to calculate Actually, maybe we should do calculate root hash. Calculate the root hash. We're gonna have a block. I'm thinking. Anyway, so we're gonna calculate the root hash. That's what we're gonna do. So first of all, what we're gonna do is if len b transactions equals 0, we're gonna return. Actually, calculate root hash. Wait, first of all, before we do this stuff, let me quickly inspect this package, right? Because we are doing stuff and we don't even know if they're gonna work. What is this package? It's gonna be Merkletree, so I'm gonna actually copy this. Hopefully it's gonna work. And I'm gonna say here, go get this thing. Perfectly fine. And then we're gonna say, what do we need? Is a Merkletree content. We're going to say list. It's going to be a slice of Merkletree content. All right. Allocate it like that. Actually, to be honest, what we could do is we can pre-allocate this, right? And it's going to be len b transactions probably. Just like that. Then we have this list, right? And then we're going to say for. Actually, we could do like that. Transactions. We're going to say list y equals question rather is. What is test content here? It's going to be a string. Actually, it just interfaces. Okay. Okay, I see. It's pretty fine. I think we could do, actually, we can maybe do b transactions. Why? We can't. Why is that? The Merkletree content. Calculate hash. That's cool. That's a problem. That's a problem. So we need to have something that can calculate the hash, but we can because our transaction is a proto buffer type, which is a little bit nasty. But what we could do is, actually, to be honest, maybe we should do. I'm not going to make another folder. It's going to be a burden. It's going to be a dependency, another folder we actually don't need. So maybe we could do something like this. Type, let's call it tx real quick, right? Actually, to be honest, I have an idea. I type the x hash, right? We're gonna call this hash, and it's gonna be a slice of bytes. Equals calculate hash, a byte and an arrow. That's fine, right? It's gonna be a tx hash, so we're gonna say func new tx hash. Actually, do we need? We don't care about this pointer, to be honest. Could it be a byte? Hash, hash. You will see where I'm going. You will see where I'm going. What's going on here? N tx hash. Not n, just the x hash is fine, right? Then we need to have two functions in here. We need to have func. tx hash. Calculate hash. It's going to be a byte and an error. And we're just going to return HH nil. And then we need to have equal. What the hell is this? Test. I need to have equal. Can we... Not quite sure if you can do that. TX hash. So now we need to have an equal because it's needed by the internal implementation, right? So we're going to say equal. Is it equal? Equals. Equals order. Order is going to be a Merkle. It's going to be content, but I was too lazy to basically select that, so I just do this. It's probably a boolean. And an error. That's nasty, but it is what it is. Error, alright. Just like this. Equals. So how are we going to check that? Can we do something like this? Equals hash equals, oh my goodness, other. Probably can't. Yeah, we need to cast this. This is so nasty. We need to cast this. Byte cannot be compared. That was what I was thinking. So what we're gonna do is bytes. Can we do equals? Huh. Bytes equal h hash and other cast is to a tx hash. And we're gonna say equals is this, and then we're gonna return equals nil. That's what we're gonna do. It's crazy, but it is what it is. All right. So, of course, now we're gonna append this to this list, but we need to have a new tx hash, and it's going to be types. It's going to be where are we? We are in types, right? How do we do that? Hash transaction. Hash transaction. B transactions. Y. It's going to be the list, right? So we're going to append all this to this list, and then we are going to calculate this thing. Let's copy everything actually. Boom. I can't. Yes, I can. So we're gonna have T. If there is an error, what are we gonna do here? Calculate the root hash. Are we going to return an error? Maybe we can. Wait, first of all, what is a Merkle root? It's a byte. That's actually insane. That's insane. That's insane. That's good. So we're gonna say it's gonna return us a byte. It's gonna be the root, the Merkle root, the root hash, and then it's gonna return an error, just because we can be compatible. Actually, to be honest, if we cannot calculate a Merkletree, we're gonna panic. Actually, no. Let's do it like this. So we're gonna say return null r in this case. Then we're gonna have the Merkle root here. To be honest, we can do return t Merkle root null, something like that. Like that. The problem is, I think there's gonna be a problem if the block is empty. If you don't have transactions, although maybe there should always, of course, can a block have no transactions? Good question. So we're gonna calculate the root hash. The thing what I wanna do is, I wanna test this real quick actually. block test here. So what I'm gonna do is func test calculate root hash t testing t. We're gonna make a block here like that. Then we're gonna say block. What's going on here? Blockchain transaction is going to be append block we don't oh proto open transaction. Yeah, I see. It's going to be can we do this? So we have one transaction, of course. It's going to be, let's make a version real quick so we have something. Actually, to be honest, let's do this. Proto transaction. Let's do version, not this one. Version. Version is going to be, actually, it's going to be a capitalized V, and it's going to be, I don't know, probably like that. We're gonna append this to X real quick. And then we're gonna say block. Wait, block calculate root hash. Maybe we don't actually need to return that stuff. Let me open up block. You will see why. Because calculate root hash, we don't care about this. We're gonna say it's gonna return an error. And that's it. We actually don't care. Return R, and then we're gonna return null here, right? And we're gonna say because we have a pointer, we're gonna say root hash. It's going to be the Merkle root, just like that. Call it a day. All right, so we're gonna say block calculate. We can't. We need to say calculate root hash of this block. All right, and then we're gonna say assert. It's gonna be an error. Actually, we could do like this: assert null t calculate the root hash of this block, and then we're gonna actually assert equal. I don't know. Actually, let me print out this block real quick because I have no clue what's going on. Print ln. All right, let's test this. We can't. What's going on? Print. Yeah, VS Code is lagging. Right, we're gonna run the test. The root hash is gonna be this one. We also have a timestamp. That's actually crazy. It's gonna be a byte. Oh no, it's fine. It's the way proto buffer is showing this. The root hash. What I want to do is I want to say len block root hash. How long is root hash? 32. That's actually fine, right? So what we're gonna do is we're gonna say assert equal t32 len block root hash, right? Just like that. And what we also want to do is verify this. How can we do this? Yeah, we can also verify for each transaction if it's actually appended in that block. The question is, do we need that? Probably we do, actually. So, verify tree, what is that? Let me see. X, VT, R is going to be... We can't, it's a tree. It's going to be in block here. Where is blocky? Calculate root hash. Root hash is going to be t verify, not content, t verify tree. a bool. Yeah, we could do it like that. The question rather is, why am I coding in two windows at the same time? If r is not null, we can return the r, and if b error f invalid root hash actually, or Merkletree maybe. Wait, what's going on? No new variables. Do we have b then? Yeah, b is block. That's crazy. Valid. I'm gonna call this a valid. All right, if valid. All right. That should be good, right? So we can calculate root hash. Let's do the basic validation here and validate block. It's probably here. Verify block. So we do the signature. That's fine. I'm thinking. We have this tree here, and before we set the root hash, we're gonna verify this tree. So I think if we do in verify block here, so first of all, we're gonna check its signature. Let's first check and this is gonna be gonna problem with a lot of tests, right? Actually, to be honest, calculate the root hash should only proto block. It's gonna be a bool actually, to be honest. So we're gonna, this is gonna be so what I'm gonna do is I'm gonna basically make it a little bit more what's going on here? A little bit more better. Nil, and it's going to be, instead of setting this, I'm going to return the Merkle root and nil, right? That's what I want to do. So first of all, we're going to say root hash error is going to be calculate the root hash, right? B of the block, right? And we're going to say if there's an error, and the error is not nil, of course, we go into return false, right? If there is an error, we're going to return false. Then we have the root hash, which is going to be, actually, that's not good. Get Merkletree, as we're going to do. We're going to return this T. Damn, it's going to be a pointer. It's a pointer, that's fine. So we're going to actually here, we're going to return T. So now we don't need to hassle with this stuff, right? With this transaction hashy thingy. So we're going to say that the Merkle tree is going to be get the Merkletree of this block, right? Shit. Get the Merkletree of this block. Then we're going to actually verify. We're going to say tree, verify this tree. If it's not valid, we're gonna... It's gonna be a boolean. Wait, what's going on here? Return false here. Return false here. And return valid here. That's what we're gonna do. Verify the root hash. So right now, we're gonna have some problems in some tests, block test actually. Where is the problem here? Calculate the root hash. We don't have it. Verify block. That's fine. Wait. Calculate the root hash is going to be get Merkletree. Wait. Verify block. Verify the root hash of B. That's what we're gonna do. If what am I doing here? If, like I said, it's all going on the top of my head. So we're gonna say gonna return false, right? If we cannot verify the root hash, we are in trouble. So basically, that's what's going to happen. Make run. We're going to have a valid, invalid stuff. Wait, make run. That's not what we want. Make test is what we want. Right, invalid block signature. That's all fine. That's because undefined root hash and block test. Let's open up the up. It's going to be... Wait. Get Merkletree of the block, that's the first thing we want to do. Then we're going to assert nil tr, right? Then we have this tree. Actually, can we not do assert true t verify block? No, verify root hash block. There's going to be a problem because it's going to pass. The problem is that this is going to be false because we don't set it, right? What we could do is in block is if we want to verify the root hash, we can basically say if b root hash. Actually, I'm going to say if len b root hash is 0, and we're going to say b header root hash is going to be tree Merkle root, right? So what we're going to do is we're going to verify the block. If it's verified and we don't have the root hash set, we're going to set it. If we already set it, we're not going to set it just to, I don't know, save some stuff. That basically means that this test is going to work perfectly fine. Because we wait, so the next thing we need to do wait, we are actually wrong. We are wrong. Let's go to block. So verify root hash, we're gonna basically check this. If valid, return false. And then we're gonna actually check if B, return B root hash equals 3 Merkle root. That's gonna be a problem. Shit, it's bytes, right? Wait, we cannot do this, right? We're gonna compare this. This is basically gonna give us a problem, right? It's gonna be failed because it's false. So I think if we're creating a new block and after transactions, or maybe after signing a block, to be honest, if we sign a block, maybe we're gonna set the root hash at sign. We're not gonna set this, right? Is this fine? We're gonna delete this. What we're gonna do. Let me open a block test because I'm not quite sure what's going on here. We need to sign it first, right? Yeah. Don't have a priv key, that's nasty. So we have a priv key, sign block, why is it not working? Because of this, right? We can make a nice var here. So we're gonna like this. We're gonna have this new block. We're gonna add a transaction. We're gonna sign the block, which also basically means we're gonna have the root hash set. So we're gonna say get Merkletree of this block if r is not null. Actually, we don't care. Let's just panic here. It's a little bit nasty. Maybe we can refactor that a little bit. Let's repanic this error here, and then we have this tree. We're gonna say, do we need to verify this? Yeah, no. Yes. No. Header root hash is going to be 3 Merkle root, something like that. Not quite sure. We could make a different function. We could sign block and then calculate Merkletree or something. But or call finalize where we do that, but I don't like it. Right, so this is going to work. Yeah, you see it's going to be perfectly fine because we set everything. We verified the root hash. This is going to set it. Fine. So the question, of course, we're going to have some problems, I think. Actually, I don't think so. Maybe everything's going to work. No, it isn't. Cannot construct tree with no content. That's true. So we have a problem here that if we have no transactions, going to get a problem. So what we're going to do here is we're going to say if, actually, we could do if len b transactions equals 0, going to be a problem. How are we going to do that? With no transactions. Do we care? A block with no transactions? That's actually impossible, right? So we need to make sure we actually have all we have transactions actually. Because it's willing to construct that, and then it's going to return a tree. So basically what you could do, get Merkletree, verify root hash and all that stuff, sign block. So we want to make this tree. We can do something nasty. Actually for now we could do if len So if there is more than transaction, then we're going to calculate the Merkletree, and the same thing we need to do in verify block is to verify the root hash. But first of all, we need to do if len b transactions is bigger than 0, then we're actually going to verify the root hash, because if we don't have transactions, we cannot verify. There is no root hash, right? Maybe that's going to work a little bit better. Okay, we still have a fail. Invalid block signature is going to be in chain tests. I see. We're a pending transaction. Yeah. Okay, I see the problem. So we are actually signing, if we're signing a block, we don't sign the block here. That's a problem. We don't sign block, right? We don't sign the block. We just do transactions, right? Wait, so why? It's invalid block signature. Yeah, of course. It's signing with the root hash. Why don't we sign the block? That's crazy. This is crazy. So this function was failing. I don't know why. Hi. Wait. What is going on? Validate block, that's what we do actually here. Verify the block. We do that stuff, that's fine. We verify the block. Invalid block signature. That's not true, right? This could be an invalid data hash actually. Right, so we need to do a little refactor here, right? Because I think verify block, I think we need to verify block and verify signature and verify root hash should be 3 different things. So the debugging for us is going to be a little bit better, right? But we have a root hash implemented. So now we are doing some more validations. We need to restructure our validation so we can see what's going on. And you can see we cannot add a block already because we have an invalid signature. So it's already very secure with all that root hash stuff and things going on, which is actually very important for our blockchain, right? That it's super secure. Right, so we need to debug that. And of course, debugging, I'm not going to skip forward or something, but the video is already 40 minutes. And I think we did what we needed to do. Of course, now we need to update our test and stuff. And that's a little bit verbose, a little bit tedious. And we're probably going to do that in the next episode. We're going to make the validation fine. And then after that, we have basically our whole security system set up, actually. Of course, not the consensus, but besides that, our blockchain is going to be very, very, very secure with all these things that needs to be in order, right? All right, thanks for watching. See you in the next episode.